Hello. All right, we're going to solve a physics problem here. A 350 kilogram roller coaster is released from rest at point A on a frictionless track with no wind resistance. Why frictionless and no wind resistance? That doesn't even seem probable. Well, it's not, but it helps people understand and begin to comprehend conservation of energy problems, which is what this is. So we remove all non-conservative forces or path-dependent forces, such as wind and friction. So on this roller coaster, we want to know how fast will the roller coaster be at point B, right here, the top of the loop of its track. And we'll get into the second question after we solve that. So how do we begin doing this? We got a bunch of these numbers here. 2 meters above the ground here, 20 meters above the ground here, 13 meters above the ground here, and 10 meters above the loop. We got to go each step solving this? That's a big problem then, which is what I just solved over here. Wow, that's really long. Do I got to do that for every one of these? Let's find out, huh? So for every conservation of energy problem, we start out kinetic energy plus potential energy on both sides, set them equal to one another. And when we do that, I just wanted to make a footnote here that the mass times gravity times the height at point A was 68,670 joules. We're going to see that recurring number throughout this particular system here. So the roller coaster was released from rest, which meant the velocity at point A was 0. Anyway, so solving this, you can pause it anytime you want to see the steps, but solving this at point 2 meters above the ground, 2 meters above the ground right there, I get a total kinetic energy of 68,670 joules, just like I got for the initial potential energy. Okay, didn't lose any, didn't gain any. Same amount. Equally, at this 13 meter above the ground point, I also got the same thing. And again, you can pause it to take a look at the steps individually, but mass, or the potential energy plus the kinetic energy, I got 68,670 joules. And ultimately, the velocity at point B was 14 meters per second. 14 meters per second. So what does that mean? Why do we have to take all those steps? Well, we don't have to take all those steps. Okay, take a look at this. And again, you can solve it at any point. Kinetic energy plus potential energy at point A. Kinetic energy plus potential energy at point B. Zero velocity at point A, cancel all the masses, because the mass doesn't change. We don't get a new passenger along the way. We don't lose anybody, thankfully. But you can take a look at these steps individually. I set it equal to velocity and started taking the steps down easily so that it's easy to comprehend. And I ultimately got 14 meters per second. Okay? And so what does that tell us? That tells us that we don't have to take all those steps over there. Okay? Don't have to do that. Don't do that. Okay? Just solve it this way, because there's nothing pushing back against us. There's nothing holding us back. There's nothing helping us. Just regular conservation of energy problem. Now, the part B question here. How hard will the roller coaster be pressing against the track at point B? All right. So in order to start that, I started drawing a free body diagram of a roller coaster on a track, minus wheels. I didn't put wheels on there. But anyway, a roller coaster pushing on a track. All right. The reactionary force of the centripetal force is pushing outwardly against this track. Okay. Force of gravity is pushing downward. We all know that centripetal force acts downward. Centripetal, meaning center seeking, is seeking the center of the circle. However, when we react to acceleration, we are pulled back, right? Whenever you put the pedal to the metal on your car from 0 to 60 in 10 seconds, which is a measure of acceleration, You are pushed back in your car. Your car is not pushing you forward, is it? Okay, so this is a reactionary force of the centripetal force pushing upward, and the force of gravity is actively pushing that cart down. And so we set it up accordingly. The force is equal to the centripetal force minus the force of gravity. And we have, again, F is equal to, and I broke it out. And I accidentally skipped a step here. I said mass times the linear velocity squared divided by the radius minus the mass times gravity. You know the mass times gravity is the gravitational force. However, where does this v squared over r come from? Well, it's actually equal to a sub c, centripetal acceleration right there. Okay, so that's what that is. Well, we don't know what r is, do we? Well, if you take a look on my loop over there, whoop, that one right there, it says simulated perfect circle. I just couldn't freehand it very well. So if it's a perfect circle, it gave us the diameter of our circle, okay, which was 10 meters. I cut 10 meters in half, give us the radius, okay. Again, it's a very ugly loop, but that's our diameter, okay. So what do we get? What do we get whenever we do that? Well, we have masses, all right. You could probably factor out the masses, but I just put it along with the equation right there. And you could probably just solve it how it is right there. I don't exactly know if it will be positive or negative. 350 times, we'll try it out, 14 squared divided by 5, all right, minus 350 times 9.81, and we get, oh, hey, it's positive, all right, cool deal. Positive 10.3 kilonewtons, okay? Let me know if that's not what you get. Anyway, that's how you solve it. Thank you very much for watching. Hey, you have a good evening, good day, afternoon, whatever.